Picking up where we left off in the last video, we were talking about finding the sum for this power series, realizing that that sum is going to be a function. We have a geometric power series in X. Let me rewrite that general term, kind of like we had been doing when our series were just in N. And so that's what that general term would look like. As a matter of fact, I could go one step further and write it like so. So this is a geometric series because it's acting exponential, and it is R. And so you can see this is where that comes from. Now, the fact that they say R is negative 1/3 x plus 1 we'll get to in a minute. But you see that that is indeed R. I have also talked about when we were dealing with series in N that the proper form when you're talking about finding the sum of your series in general should be that form. And then when you expand it, you're guaranteed to have A, which, A naught, plus A sub 1 R1 plus A sub 1 R squared, and so forth. So I want you to realize that if we just go back to this series, even though it starts at 0 and goes up to infinity, in N, we can generate those terms, and the first term will be A, and the second term will be A times R, and so forth. So when N equals 0, I'll just write it all down. That's negative 1 to the 0. I'm going to use this form. X plus 1 over 3 to the 0. And then when N equals 1, that's negative 1 to the 1 times x plus 1 over 3 to the 1. Give myself a little more room here. The next term would be negative 1 squared times x plus 1 over 3 squared, and so forth. So you can clearly see that the first term is indeed 1. That's not an issue. And the second term, which is A times R, which is where they're getting their R from, if A is 1, then R has to be that term. That's where they're getting this from. I don't want you to be confused because I spent so much time making sure that you had your geometric series in the proper form of, to the n minus 1 right here. I wanted to make sure that you had it in that form. So you would definitely find A and definitely find R. It turns out for geometric series, and really any series, but in this context, it's okay to just generate the first couple of terms and figure out what A is and figure out what R is. And then we're going to go back here, and we're going to use the fact that we know for any geometric series, the sum is A over 1 minus R, where A is 1 and minus R. R is negative, right? We could write it that way. Might be easier to write it that way. And then we can clean it up some. 1 over 1 plus x plus 1 over 3. We could multiply this by a well-chosen 1. This is actually a function in X in and of itself right here. I mean, if it was a free response question, you could walk away right there. But if it was multiple choice, you're probably going to see something that might look a little more like so. So there is the function that is the sum of this geometric series. Okay? So pretty straightforward. Power series are not difficult to deal with at all. So we shouldn't have an issue here. Another way to determine or to prove or to show that a function is the sum of a power series is to generate it. Generate from the function the first, let's say, 4 non-zero terms of your power series, and then generate, using what we know about series in general, the first 4 non-zero terms. And they should match. So let's do that. Here is f of x. F will need f prime, f double prime, and f triple prime at least. E to the x is its own derivative. The question here is, at what value should we evaluate those derivatives? Where is our center point of question? Why am I saying it's 0? Well, there's a huge clue right here that I'm centered at 0. And you may have to make that connection. E to the 0 is 1, 1, 1, 1. All of those are 1. So none of them go to 0. That should be enough for us to generate the power series for e to the x. And so it is 1 plus 1 times x minus 0 plus 1 over 2 factorial times x minus 0 squared. So I could even write it like so. And then the next term, 1 over 3 factorial times x minus 0 cubed, or x cubed over 3 factorial. That's probably enough to convince us that if we do expand, starting at n equals 0, this nth term, and we get the same first 4 terms, that's probably enough to convince us and an AP reader that we have indeed found or shown that the function is the sum of the power series. So let's do that. When n starts at 0, we have x to the 0 over 0 factorial. Then we're going to have x to the 1 over 1 factorial. Then we're going to have x squared over 2 factorial. Then we're going to have x cubed over 3 factorial, and so on. Remember me telling you that 0 factorial equals 1. We know that anything raised to the power of 0 equals 1. So that first term is indeed 1. It is true that 1 factorial equals 1. So that's x over 1. And then you can see very straightforwardly the other terms already look exactly like the terms we found. So it is true, and we have shown that e to the x is the sum of that power series. Make sure that you recognize these two things in general, that a function is equal to its power series as long as that power series has infinitely many terms on some interval really close to that target point that the power series was built around. And since the power series is an infinite series of some sort, like so, that also is going to equal the function. So the function equals both of those in general. This is an extremely powerful symbol. If they're equals, that means that we can substitute one for the other. So make sure, in general, big picture, that you understand that the sum of any power series is a function, and specifically the function around which the power series was built. Okay, I think that's enough for power series and their sums. You get an idea. We begin to tie back into that polynomial work we did right at the beginning of our series work. The next few lessons will tie even more into all of those series tests that we found. So come to class next time and we'll work some homework problems.